Fine. Okay, so our last speaker of the day and of the workshop is Paolo Valente from University of Modena Reggio Emilia, and he's going to present us an interesting work about how to reduce the latencies in I/O and disk accesses again. Okay, thank you, Paolo.
Okay, so first, sorry for being late. I had a visit from one of my children and it started late. So I wanted to show you two contributions that I made for Linux, let's say. So it's also something also about papers, but now I would like to focus on Linux contributions. So the first one is about packet scheduling, and it's basically a modification scheme to reduce the cost of a certain family of packet scheduler, which ones? The fail queuing packet schedulers. And the other thing that I'm going to show you is one of the schedulers that I obtained by applying this modification scheme to a specific scheduler. And this new scheduler is Quick Fail Queuing Plus, which whose name with much fantasy comes from QFQ, and added plus because it has a lower computational cost. So I applied this modification scheme to QFQ and obtained this QFQ class. So QFQ was already in Linux. I first defined the QFQ a few years ago with Fabio Checconi, which I guess some of you know, and after a few years it entered mainline, Linux mainline and FreeBSD. Then I had this idea of this modification scheme, so I defined this new version with a lower computational cost, and it replaced the original scheduler in Linux, while in FreeBSD there is still the original one. One thing which will become useful later, the name is the same. In Linux, the scheduler is QFQ+, but the name of everything, the file and so on, is still the previous one. Okay, so why did I do this? There are very efficient fail queuing schedulers. One of them is deficit round robin. They have a very low computational cost, but they suffer from a high packet delay and a high jitter, which is worse. Delay with respect to what? With respect to a perfectly fair and smooth service. So this is on one side. On the other side, there are schedulers which are much more accurate. Some of them are even optimal in that they guarantee the minimum possible deviation with respect from an ideal service. Others are near optimal, let's say so. But the problem is that even the fastest of these other more accurate schedulers is at least twice as slow as deficit round robin. So this was the motivation for this reduction of the complexity of this scheduler. Okay, so what's the idea of this modification scheme? It's definitely simple, nothing particularly new. Just group packet flows into aggregates and perform the operation that are more costly, the operation of the original schedulers, on aggregates instead than performing them directly on flows. To reduce, so we moved these operations from flows to aggregates. The other step is performing these operations less frequently. How to achieve that? By just serving each aggregate for a relatively long time. So the frequency at which I execute an operation to decide the new aggregate to serve, and this is the costly operation, goes down. Of course, there are flows inside each aggregate are still to be scheduled. And in that case, the scheme, according to this modification scheme, the scheduler used is just a deficit round robin whose operations are quite cheap. Okay, so benefits and drawbacks of this modification. The higher the number of flows is inside each aggregate, the longer each aggregate is served before deciding the next aggregate to serve. So the less frequently costly operations are executed. So this is the benefit. The problem is that the higher the number of flows in each aggregate is, so the longer each aggregate is served, and the higher the deviation with respect to the ideal service is, just because guarantees become coarser and coarser, because aggregates are, how can I say, larger than just flows. Basically, the idea is that the sum of the packets served for each aggregate are seen as a sort of super packet. So the more I serve each aggregate, the longer this packet is. Since this service is non-preemptive, the coarser guarantees become. So to go on, I'm not about to show you diagrams and so on, but directly QFQ Plus in action. Of course, there is a downside, because what I'm going to show you is not as precise as diagrams would be, but this is the choice that I made. In the video that I'm going to show you, I will not consider the old QFQ. For several reasons. One is that you can find it only in older versions of Linux, so it's in a different environment with respect to the new versions. And the other problem, I also tried to go on porting it to new versions of Linux, but it was quite time-consuming and in the end useless. So in the video, I will compare QFQ Plus only against the deficit round robin. So this is what I'm going to show you. It's a test with a pair of virtual machines, a generator, and a sink. These are the characteristics of the physical machine on which I run these virtual machines. The bandwidth of the output link of the generator was limited to 300 megabits per second, and the purpose was to not saturate the CPU bandwidth on the machine, so that the results are not affected by things that are unrelated with respect to what I want to show you, that is the actual accuracy of the service provided by these two schedulers. So this is what first I'm going to show you the computational cost of this scheduler. So on one window I will start the test, and the other one, start the part of the test on the generator. This is the receiver, and this is a measure of the utilization of the CPU. This is how a simple way to show the computational cost, usage of the CPU. As you could see at the beginning, the other percentage was 100%, so the machine was completely idle. I tried to keep the machine completely idle. What else? The sources are 500 TCP sources, then plus 500 UDP sources. Of course, on the other side, there are the corresponding receivers. And that's all. So this is the results. This is exactly the same test. On the top window, on the top part, there is QFQ, which means QFQ Plus. This is why I told you at the beginning that the name is the same. And here, deficit round robin. We are going to see the CPU usage. And Of course, there are fluctuations at the beginning, but after a while, the values will stabilize. You can already see that the idle percentage with QFQ Plus is higher, and this should be the final value. 50% of idle percentage with the QFQ Plus and about 40% with deficit round robin. This is a curious result because one would have expected the deficit round robin to cost less than a more accurate and complex scheduler. Basically, the reason is that thanks to its smooth service, QFQ Plus is more cache friendly than deficit round robin, because the service of deficit round robin is more bursty, and in many cases a more bursty service is less cache friendly than a smooth one. But then if you want to know more details, okay. Then service guarantees. To show you service guarantees, I used this demo. Started a video streamer on the generator virtual machine, and a player receiving the video on the other machine. At the same time, I started, if I remember well, but we're going to see it, several UDP flows, because they are the more greedy ones. And I'm going to show you what happens. So this is the test. Okay, this is the bandwidth of the link, limited in this case to just 4 megabits per second. And you are seeing the playback here. There is no glitch, and the video does not stutter, no artifacts, nothing. The playback is perfectly smooth. This is with QFQ Plus, and now, as before, a comparison between the two schedulers. So here again, QFQ Plus, and here deficit round robin. Everything else is identical. Same bandwidth, same disturbing flows, everything is identical. As you can see, it stopped while I was talking, stopping again. Stopping for a while. Now it is lagging behind with respect to the other playback. There are problems with the colors, artifacts, problems of any kind. I think the video will go on till just the next demanding part of the video, and then it will stop. And the playback will be perfectly smooth also in the demanding part in case of QFQ Plus. Whereas there will be a lot of problems with deficit round robin, as we are going to see in a moment. Okay, this machine is more demanding, and it's arriving also here. Okay, it blocked it just for, okay, and as you can see, completely stuck. Okay, should finish in a moment. I can also let it finish, force it. Okay, that's all about QFQ Plus. Of course, I have more slides if some of you want more details, more technical details, numbers, and whatever. Open problems. One of the problems with QFQ Plus is that, okay, it depends on the point of view. This may be a problem. It is based on the classes provided by the traffic control infrastructure of Linux. This program is in Linux. This infrastructure is memory consuming. The state to keep for every flow or class is relatively large. And the other problem is that flows, classes, filters, and whatever must be defined manually. And it's not automatic. So this is one of the open problems. The other one is that QFQ Plus does not take into account issues related to buffer bloat. I don't know how many of you know this problem. So it's basically, correct me if I'm wrong, because I'm not an expert.
No, I'm not an expert either. I know about buffer bloat. I know what it causes it, but I'm not working on that one.
Good. This is good for me. Basically, how can I say, critical flows, critical packets when you experience high latency with your internet connections, most of the times the problem is not in the internet, but in your PC or in your phone. Because critical packets for latency are just stuck in your machine for buffer bloat problems. Okay, they just stuck in your queues. So what I would like to do in the future is as for the first problem, implement an alternative infrastructure, an alternative way for classifying flow, something that is internal to the scheduler, automatic, and with the minimal states. Basically, if you already know this other packet scheduler here, I'm thinking more or less about the same solution used in stochastic fair queuing, where there is.
Is that the one Kenny did?
Yeah. Yes. Yes. So it's an hash table, okay, based on the header of the packets. So as for the other problem, I would like to integrate some mechanisms inside QFQ Plus to, for example, prioritize flows carrying ACK packets, which are basically the ones more related to this problem. And if any contributions is more than welcome of any kind, should someone be interested into contributing to this project, of course I'm willing to help him or her, and of course leave all the credits to who will do something. And that's all for the first part.
Yeah. Do we want to do question? What do we do? What do you prefer?
I don't know.
Yeah, let's make question of this, and then if you.
Okay.
Okay, yeah, that's the first thank for the first part.
I will.
I think it's better to take question on this part, and maybe.
Yeah.
Okay, so if there are any questions, or if you want to keep all yours today.
So it's basically the same as.
Okay. Now Paolo Valente presents.
Okay, and so for the other part, is this machine connected to internet?
Yeah.
Okay, so maybe I will use one of the links. So this is instead a scheduler for storage I/O. It's called BFQ again, with a lot of fantasy. What is this other scheduler? It's I think it's a production quality scheduler. The peculiarities of this scheduler is that it guarantees a higher responsiveness to interactive applications. I will show you what I mean again with another demo. It also guarantees a low latency to soft real-time applications, to time-sensitive applications. And finally, it preserves a high throughput, also with virtual machines. Another characteristic of BFQ is that it guarantees to each application the desired device throughput, the desired fraction of the device throughput, which is different with respect to guaranteeing the desired fraction of the device time. Okay, there is the link to the home page. BFQ, over the years, several distributions started to use this scheduler. Some of them as the default I/O scheduler, like Manjaro, OpenMandriva, the one that you can see. Also, this happened also with some kernel variants. Also, other kernels for smartphone are using BFQ as default scheduler. It's also available optionally in other distributions. And about 10 days ago, I submitted it to the mailing list. I don't know what I'm about to do, but I would like to show you the. Okay, it's Control C, I guess. where do I find
web browser. Yeah. Firefox.
It's starting?
Yeah,
On the
left.
The left. Firefox web browser.
Oh, okay.
Okay.
And yesterday the archive was not working. I don't know whether. What about Control C and Control V?
Work.
Okay. It's, where is it? Okay. Okay, I just wanted to show you one part that I found instructive. It was the exchange of opinions between two of the developers. And forget about details, technical details, and so on. I don't know whether you are also following this link, but I found this is the okay. Let me try to increase the. I don't know whether you can read. This is the less violent part of the thread. After that, with my poor English, I had to look on dictionaries, some of the words and phrases not very formal used. Fortunately, it was not against me. So, but for me, it was really instructive and was really scared thinking about being me on that side. And the other thing that I wanted to tell you before getting you to sleep with my demo is that it's for me it was a very profitable project. I added this donate button at the bottom of the page, and I earned really a lot of money. I don't know whether you can see. This happened in about 3 or 4 years. And it was because of one donation. Unfortunately, there was a huge fee because I think it was $5 and not just $4.50. And
so the guy even got the fee,
yes,
$5, and then
yes, I discovered that there is a fee also on free donations. I did not donate this to myself, but no.
Take a name, come on. Come on. Your friends, please donate me and then I'll give you.
So again, I want to show you the performance of this other scheduler with a demo. This demo was finished yesterday evening, so I hope I will not make too many mistakes telling you about what happens, because the reason is that I made the first demo, I think 2 years ago now, yeah, but it was with an hard disk. So I wanted to do something more updated, and so I repeated it on an SSD. Okay, that's all. And but this time I made the demo with the help of a volunteer who actually recorded it. So this is, I will try to speak on the images, let's say so. The demo was recorded on an SSD, a Plextor SSD. I will show you, the demo will show you the performance of this last version of BFQ. This is the last one, compared against the schedulers that you can find in Linux. Okay, I want to give credits to Arianna Vanzini, who actually set up the demo starting from my previous one and actually recorded it during night.
Valente is also the one who made the
Yes.
aesthetic demo I talked yesterday.
It's an example of a multitasking woman. She does everything. I don't know how she succeeds. Okay, that's all. And this is the setup. So there is a window from which I will start the applications to show you responsiveness. A window from which I will start some background work. I say I, but it's Arianna in the demo. So, some background workloads. From here, there will be the switches between the schedulers. And in this terminal, you can see the current scheduler. So the presentation starts with CFQ and goes on with CFQ most of the time because the first part, it's divided into 3 parts. A part about responsiveness, one about latency for software time applications, and the last one about throughput. CFQ is the best performing scheduler in terms of latency. So in the first 2 parts, I will compare the performance of BFQ only against CFQ, because believe me, the other ones perform worse. Okay? But if you don't believe, I have numbers, diagrams, and so on. And finally, a monitor which will show us the throughput of the device. Okay, the peak was around 500 megabytes per second, and then you will see what is about to happen. So now a terminal will be started repeatedly with call caches to get predictable results and to perform a fair comparison. And this is the time needed to start a terminal. The application is a terminal, and you can see it here flashing. It's going already too fast for me. Let me show you first the simple part. So from the top window, we'll start the application. You will see it flashing here, and the startup time will be shown here compared against the startup time with an idle device. The device is idle, and now the time is the same. From here, CFQ is the current scheduler. So now I will start the reading of one file. One consideration, there will be no writes in this demo, just because we bought a new SSD and we want it to last at least a few months, so it's only reads. Okay. Okay, so the reading of one file, and I'm going to show you what is about to happen to the startup time of the terminal with just one file being read. You can imagine it as part of copying one file, or the system, again, part of the workload needed to update your system, or your system being some index of some daemon of your system being updated, and so on. Okay, so as you can see with the idle device, the startup time was very low, and this is what happens if you start just reading one file. This is a fluctuation, then the number should become better, but let's see. Okay, this is the stationary value, and it is about 10 times higher than the base value. But if we start reading 2 files in parallel, so a slightly heavier workload, this is what happens. This is with CFQ. So you try to start the terminal, and you wait. The SSD is very fast, as you can see from the throughput. It's not a matter of slowness, but this is the time that you get. So you may say, okay, it's normal, there is a lot of I/O going on, I have to wait. Now, apart from being very nasty against CFQ and showing that the problem persists, wait. Now we switch to BFQ. So same workload, BFQ. Here is what happens. Again, the startup time goes back to just twice the startup time with the idle device, which is basically due to several fluctuations, but I don't want to bother you with the details. we can move to 10 files in parallel to see what happens with such a high overhead workload, but the responsiveness remains the same. If we switch back to CFQ, the system, in this case only the application, is just unresponsive. With some writes, you can get the entire system to become completely unresponsive, which is bad in a demo because you cannot get again the control of the machine and go on with the demo. Switching back to BFQ allows you to let the application start immediately. So this is about responsiveness. The next part is about latency for software time application. I'm going to show it to you through the drop rate experienced by a video playback. Again, 10 files being read in parallel, BFQ, and the movie starting. I don't know what is going to happen about stuttering and so on, because one of the problems, if you see the demo live, the playback, believe me, is perfectly smooth. But playing back the recorded playback is a problem. We tried to improve it, but how can I say, it was 8 hours ago, so we didn't have much time. We had also to sleep, and so. And as you can see, in addition to the 10 files being read in parallel, we added again the startup, the iterative startup of the terminal. But also with all this workload, the playback just goes on without any problem. It will go on up to the beginning of the more demanding part, just to show you that it's not due to the fact that this is a basically static scene, and so there is not much request of throughput, but also on the next demanding part, the video will be played back without any problem. This part here. After stopping the video, in the demo we will switch to CFQ and do the same. So stop everything, okay, restart, so switch to CFQ, restart file reads, restart the playback to see what happens to the playback. I don't know whether you already guess what is going to happen. It does not start. Just does not start. So there is not much to see about drop rate because it just does not start until we switch to BFQ, and at that point the video starts and it is played back without any glitch. The final part of the presentation is about throughput, because the last question that one may ask is, okay, but what price do I pay in terms of throughput? As you can see here, apart from some small time intervals, the throughput was very high during all the time, but this is now an only throughput test. 10 files being read in parallel, and you can see here the throughput with BFQ. Now we will switch to CFQ, and as you can see, the throughput does not change. And finally, the last question is, oh, okay, but with the deadline or not, the throughput is higher. So there is the throughput the same, and the same also with the knob. This is with sequential readers. Random readers are another story. And that's all also for this demo. And I don't remember, I think there is also here an attempt to ask for help. So if some of you wants to know how this is achieved, I'm willing to tell it to you, but I don't want to steal your time with these details. I just wanted to tell you what is going on. we are investigating issues related to multi-queue, which is the current trend to achieve a high throughput, and which is a serious problem to provide latency guarantees. As many of you know about multi-core and many-core systems, it's the same problem, just with I/O. Another line of, let's say, research is how to guarantee a more stable latency in the presence of write-offs, which are serious problems, which is related not only to the scheduler. We are also investigating ways to further improve responsiveness and reduce latency, but never mind about the details. And on the opposite side, some companies asked us to do the opposite. They don't need application to start quickly. They need writes to be completed quickly, because their problem is guarantee that certain information gets stored as quick as possible. So with the same mechanism, you can get the opposite result. Okay, with the same mechanism that are inside the BFQ. And so for this, if someone should be interested in any form of contribution, is welcome. And I think that's all also for this part.
Okay, thank you.
I recovered the time. No.
So is there any question about the feature?
Yeah, can you improve read and write at the same time without one paying for the other?
Good question.
Is it possible?
I have to think about it. Thanks for the question. I don't know. I don't know. I should think about it.
A large part of the write problem is also the virtual memory subsystem.
Yes. Yes.
And that's
Most part of the problem.
Yeah, it's in a whole better shape than it was several years ago, but we still have some work to do.
There is something that can be done also at the schedule level. Tejun, I don't know the correct pronunciation of his name.
TJ.
Tijen?
TJ.
TJ, okay. I don't know whether I can call him. He proposed something that we already talked about, and the idea is quite simple. The block layer asks to the scheduler whether it can get a given request. If the scheduler says no, that request, you cannot get it, maybe the scheduler can somehow have a higher control, at least on responsiveness, by just slowing down the request of I/O requests, and so the saturation of the pool. This is one of the this was the idea we are thinking about.
Yeah, so in San Francisco earlier this year we had the file system storage and memory management summit. And we basically discovered that the principal feedback mechanism, which is device saturation, doesn't work because devices never report their saturation.
Exactly, and it also fluctuates very quickly.
Yes.
We tried also that. Our problem was basically fluctuation. When you think that it's saturated, it's not anymore, and so you.
Yeah, and Dave Chinner was going to look at the synchronous write issue because a lot of people want that for their database.
Yes.
Yeah.
Yes. But then throughput goes down. But maybe someone is happy also if the throughput is low because they just want guarantees on the time to completion of the writes.
They need their log file written. If the log file isn't committed to disk, the whole thing writes to a hold. So
yeah,
it's important to get them out.
Yeah.
Any other question, comment? No? Okay, so we can thank Paolo again.
Thank you.